that has the notion of a function, you would have a separate area where you say, this is where I define my functions, this is what name it is, this is where it starts, this is where it ends. In AVM1, it is an instruction for the virtual machine. So functions are defined by executing them. There is an instruction that says, I'm a function, and the next like 20 bytes is code of me. And then the interpreter just like, the virtual CPU just like goes over the 20 bytes, reads them in, and then there's a new function. This, of course, can be nested, and they can be executed in line, so you define a function and it's right away executed, anonymous functions. So this is just totally off the record sick. Well, they liked it so much that they implement their try-catch finally blocks the same way. So there is an instruction that defines try-catch finally in line when executing. This is obviously has a lot of design weaknesses. So to verify code, the first thing you want to verify is it doesn't jump in the middle of an instruction. Many of you have probably seen that in x86 code being done for obfuscation. You can totally do that in Flash as well. The funny thing is you can also just jump into the tag right before you in the flat file and execute some code in your MP3 or whatever. Like hide your code in the nipples of the porn and then jump right there. In the image data, no problem. They do that. The 16-bit branch offset is also a interesting design decision. So I was wondering, when you have 16-bit signed, you can only jump over like 32K, right? Because then your bits run out. And so I was wondering what they do if you have an if statement with a large body. So I took the official Flash player development environment, latest version CS4, and made an if statement with a large body. It never complained, it produced a Flash file, it is perfectly invalid code because it jumps as far as it gets and then executes the rest of the body. The various length fields in the instruction set allow you to hide a lot of data in the tail of the instruction, and that's commonly done in Flash code obfuscation software. So, and as I said, the order of code execution is highly dependent on where the shape of the asshole currently is. So this is where Blitzableiter comes in and disassembles the whole thing and verifies a lot of things. So what we do when we disassemble it, the first thing we do is we go from byte offsets to instruction indices. So all the disassembly is an array, and if your byte offset actually doesn't resolve into an index in our array, then you're jumping somewhere you shouldn't jump to. And we are verifying the code flow stays within this code block, and we verify all kinds of crazy shit about like this function declaration bullshit, so they're not overlapping, and all of that. And down to things like our all instruction only part of exactly one function, stuff like that. We just make sure it's good. Now, once we made sure it's good, we still have that problem that, remember when I talked about the ad networks and people that receive Flash files? For them, it's not a malformed Flash file, but functionality that can be implemented in Flash AVM. So how do we actually get functional attacks to not work anymore? Now we have a nice and tidy Swift file. We could run static analysis on it, but static analysis provably will not resolve all possible cases, so we will not. It can be shown that we cannot possibly predict what the code is going to do. It's called the halting problem. Look it up. If we try to emulate it, we will run into the problem that our emulator does something and the Flash player does something. And if our emulator isn't sick enough to be Adobe compliant, then we're actually like going two different ways with the code. So that's also not a good approach. However, when you do runtime analysis, like if you have the specimen, what you usually do, runtime analysis, anywhere in disassembly, you set a breakpoint at the point of execution, let's say the syscall. And no matter how much obfuscation was going on before and how complicated the argument was compiled together, at the point of the syscall, you just set a breakpoint and you see what the argument was. So we want to do the same thing with the Flash files. The problem is we're not part of the show anymore. when the porn gets played, right? We already produced an output file. We are not debugging the Flash player. But what we can do is we can actually patch the AVM code to do the check we wanted to do right at the point of execution. And this is what we do. So here's an example. There's action get URL to second attempt in getting the opcode right. That actually is the most common function that forwards your browser to a different URL and is used by most of the downloaders, like the Flash downloaders that just download like scareware onto your machine. So when we handle the Flash file, for example, we know its origin. We know where it came from. No script passes this on to us. So we can actually patch more strict same origin policy checks into the Flash code itself than the player would actually do. And this is how it looks like in a code flow graph. So on the left-hand side, you see a basic block graph of AVM1 code, and pretty much in the middle of it, there is a block with the ID 31, and this is where the actual execution of the action get URL happens. And before that, he's pushing the arguments on the stack. In this case, for example, it's pushing arguments out of the constant pool on the stack. I'm coming back to those cases in a minute, but just notice that there's this one block where the actual action is fired. All opcodes start with the word action, so don't feel silly or like a movie producer when you work with this shit. It's totally normal to say action every 5 minutes. So when we patch it, this is what comes out. So you see that the one basic block with the ID 31 was split into 3. The upper one doing the validation and a string comparison, a strict string comparison between where the Flash file came from and where it wants to forward to. And then if it's happy with the comparison, it forwards the browser. If it's not happy, it's just cleaning up the stack and not doing it, which is what we wanted. So just to give you a feeling, there's a complete assembler for AVM1 and 2 in Blitzableiter. You can write Flash assembly and text files and use that as a replacement, so you have a pretty high level of freedom. So this is the assembly for AVM1 to how it calls methods, and on the right hand side you see all the instructions you need to execute to even figure out which method of which object is called. So you see it's a lot of code that goes into just finding out what the method of the object was. And if you actually decide to not call the method of the object, that's the amount of code that you need to clean up the stack and do stack unwinding in AVM1. So when you apply this to a piece of malware, example Gnida, you see this is the complete code of Gnida. The one to the left in blue is the original code. The one to the right is the same code, and all the red dots and places you see there, this is where we patched in additional checks automatically. You see it's quite a code inflation, so we're looking at 250% code inflation just to check that it's not doing something evil. I mean, it's still nice because it totally protects you. Every single call is protected, but it inflated the code way too much, and so maybe the porn starts no longer being fluent. And you also run into problems with the signed jump targets, because like the stuff you patch in is too big, so you can't jump over it anymore. So therefore, we introduce static analysis into it. We can provably not determine every single call argument, especially not the dynamically generated, but we can try to prove the static generated. We can prove staticness for individual arguments. For that, we just need stack tracing. So what we do is we trace the stack back on the individual instructions, and if we can tell it's a static argument, then we do the check right there and don't patch the check code into the Flash file. In order to determine the values, we actually need to obtain a code flow graph as well, because of course the constant pool is not part of the file format, but it is another instruction. So since the constant pool creation is an instruction, you can actually overwrite your own constant pool in your own code. So we actually have to do a complete code flow analysis in order to figure out which constant pool currently is on. On top of that, we're still a little bit working on, but it's already part of the code, on higher level verification. So you can essentially say, this is the object, this is the method, and I want to have the following string comparison with the second argument of this method call, no matter if it's AVM1 or 2. And how that works right now is we have our own virtual machine, actually 2, which get executed with individual parts of this question, like give me the second argument to this instruction here. And there's 2 possible cases. It's a static analysis engine, so it executes this, this step and tries to figure out the second argument. If it cannot provably figure out what the second argument is, or it can prove that it is a dynamic argument, then it will emit the respective, then it will stop execution, and then we run the same process again, but in a different mode. Instead of trying to prove staticness, it will actually emit the steps that it took in the first run as AVM1 code, or AVM2 code. This allows us to have very small pieces in those steps and ensure that our static analysis tests and the tests we do in the actual AVM1 code are functional equivalent. Because otherwise we run into the problem that we test something different here than there, and that's not very useful. So we recently introduced AVM2 into Blitzableiter, so both AVMs are now covered. There's an interesting bit about the AVM2 specification, the ABC file format that I said they put complete file format into the file format. So there's an interesting thing here. There was apparently one one-eyed guy between all the blind. And he wrote the specs, so he tried really hard to be smart, and he actually had a good trick to prevent all his less talented colleagues at Adobe from having integer overflows. He will actually put like all the length fields and counter fields are 30-bit, not 32-bit. So if you're an untalented programmer, you can add 4 of them and still not have an integer overflow. That is actually pretty smart. However, when you take the official Tamarin is the open source implementation of AVM2, and it's pretty much the official thing. So it's Adobe people writing it. When you look into that, how they parse it, this is their C code. Of course, they write it in C. Nothing can possibly go wrong. This is how they parse the 30-bit field, and if I may direct your attention to the third line at the bottom, they're actually parsing 32-bit. So this one guy was actually pretty smart, but yeah, he was pretty alone. Other than that, AVM2 is design-wise a lot closer to its predecessor as it should be. They finally figured out that you should have one constant pool, and they finally figured out that you should not define functions by instructions. I'm very grateful for that. The stack tracing is a little bit harder, but it's, yeah. So the end goal is to really have it all unified, so for whoever wants to enforce rules in the code, that the definition is high level enough for them to model their contractual requirements into actual code patches. So what happens when we use our tool? So far, not a single exploit that we have a specimen of actually managed to pass through the Blitzableiter tool. Most exploit code, as you've seen in the demo, doesn't even bother to set the length fields right, so we cache it very early. But even those fixed actually never went through. There's 2 where I don't have a actual exploit. Which pretty recent from this year that exploit JPEG parsing. So they even managed to fuck up the JPEG parser. This one would state right now still pass through because we're still not validating media content within the Flash file, but all the others were blocked. And all the recent vulnerabilities that came out were automatically blocked because we don't need fucking signatures.